How are we doing today? Doing all right? Ready to get going with the real stuff here? Okay. A small update uh, from the stuff that I was emailing through Blackboard about last night. By the way, is everyone getting those emails when I send blast emails through Blackboard? Okay. That'll be how I send messages outside of class. A lot of that information kind of week to week is more meant for the half of you that aren't here that are enrolled in the online section, but I record these lectures so that they can go back and review it as well as you can if um, you would like the opportunity to do that. So the big outlines aren't necessarily meant for you, but they're helpful if you want to kind of use that as a guide. And a lot of that stuff I will say in class probably, um, but that's what's going on with that. It's kind of a scheduling guide to make sure that the folks who don't come here every other day um, know what's going on. But the thing that I was messaging about yesterday was to do with the thing that I apparently screwed up when I tried to make a link in Blackboard for the ebook. I didn't have time to sit with them the whole time while they're investigating the issue, but I got in contact with the folks who manage the textbook company people. So they're looking into it. Hopefully they'll fix it today. If not, then I will check back in tomorrow during their office time to try to get that resolved. Um, I think it's a combination of there's something that's not working as intended, and also I definitely clicked at least one wrong thing. So some of it's my fault, but I don't know how much is my fault. Anyway, that's what's going on with that. Hopefully it'll be resolved soon. When it is, I'll re-enable a fixed version of that link and let everybody know what's going on. Um, but that's status for that. Yes. What I will do for the quizzes, the this little small snafu with the textbook is interfering with things a little bit, and this is also the first week, which I'm not going to run typically for us. This question has two answers. Okay, one for the online folks and one for you all. I will, depending on what week it is, either give a online type quiz, which will be basically just like a short selection of the homework assignments. That will be due Sunday evening or something. All right. And I'll typically post it around today on Wednesday. So there'll be a 4 or 5 day period where you have the opportunity to finish that up. Sometimes we will instead just have short in class quizzes on Friday. That'll be 2 or 3 problems from the assigned homework. Okay. So we aren't going to get an actual homework problem. We have small. Correct. Yes. So the the listed homework problems in the syllabus are meant to tell you what sorts of problems to expect on the quiz. Whether, since this is an in-person class, that quiz is going to be a short quiz on Friday or a online quiz that you turn in through Blackboard. You will know on Wednesday. This week, for you all, what we're doing instead of the quiz is we're having our sort of chapter 12 pre-test thing. All right. So it'll be a little bit longer than usual. I'll probably give you until Monday evening to turn that in because it's going to be posted probably not today. I'll get it posted by Friday, and then you'll have the weekend and then all day Monday to finish that up. Okay. Usually quizzes will go up on Wednesday and be due Sunday evening. And the extra credit problems also will be turned in with the quizzes. I'll probably still accept those on Monday because we're going to have a little bit of flexibility on exactly how the quiz part works. So if I give a paper quiz, I will still accept extra credit problems turned in here on Monday. But if the quiz is turned in online, the extra credit problems need to be attached to your quiz submission. Yeah. I will collect them and then figure that out. I'll just adjust your grades or maybe just wait until Monday to grade the quizzes until I have all the extra credit problems and then put everything together. The way that the extra credit points are going to be counted is I will just add a point to your quiz score for every complete correct extra credit exercise. Yes. Yep. Yeah. So for the benefit of those listening to the recording, the way it works is the quiz grade is your homework grade. The homework problems are meant to help you prepare for the quizzes, and then the extra credit problems will be a small bonus to that score. If you do every single extra credit problem, you'll get something like 10 to 15% above maximum for your homework grade for the semester, which will be worth like a plus minus level on the overall course grade with the way that homework counts. Obviously, if you look at the syllabus and look at the way that things are weighted, doing well on the exams is the easiest way to get a good grade. It's the most efficient way, we'll say, to get a good grade in the class. That's actually one of the interesting transitions that we've sort of experienced education-wise over the past couple of decades is homework at some point transitioned from being the thing that you did to practice and learn the material to this way to earn points in a class. You have to build up like this wall of points in order to succeed and get a good grade or something, which at least at the university level, I don't think is a very good model for setting things up, because we meet so much less often than we would in, say, like a high school or other type of secondary education format. But interesting pedagogical question to think about if you teach classes and stuff. I'm not sure we know the full answer to that yet, though. Okay. I should probably stop musing and start teaching math. All right. So we are going to be finishing up the last couple sections of chapter 12 today. I'm going to do a few examples. I'm mostly going to kind of give a quick overview of these things. This is part of the material that you should be looking at to review to prepare for our pre-test thing tomorrow, or on Friday, rather. But there is some important notation, and I want to point out some of the more important ideas that will be underlining what it is we do for this, because lines are really important. So we'll work with these things here. Okay. So your book has a sketch that I will do a very poor job here of recreating. We have some point, sorry, P naught over here, and some point over here, which we'll call Q naught. I guess I could just call them P and Q, that's fine. Anyway, we draw a line that connects those 2 points. I haven't used my tablet in months, and it's obvious because my lines aren't very straight. We have this segment here connecting these 2 points, and there are a couple of things that we need to be aware of when it comes to how we think about lines in space. Okay, because there's 2 different pictures simultaneously that are important. Okay, when I talk about a line in space, a line that connects 2 points, this is probably what you think I mean. Right? We have 2 locations in 3-dimensional space, and this is what's going on. However, there's another element to this that we need to be aware of. Okay? And that is the fact that actually, when we're thinking about this in terms of calculus, what we're concerned with are the vectors that are associated with what's going on here. Okay? I have a vector that stretches from the origin to my initial point. Okay? And I have a vector that stretches from the origin to my terminal point. This first vector we will call R naught. Okay? This second vector we will call R. All right. And there is the vector that connects those 2 points. Okay. I know the orange is harder to see than the other colors, but are those colors okay? All right. I get into trouble if I try to do stuff like use green. Some people can't see that. The other problem is the projector changes the colors. They look different on my screen than that one. It's no good. I forgot to silence my phone. All right. Okay, and then this other vector we will call A, we'll say. The displacement vector from R naught to R, or from P to Q. Okay, now if we use the property that says that vectors that point in the same direction and have the same magnitude are equivalent, then I can actually think about this vector A as being a parallel vector down here that starts at the origin and moves in the same direction. Okay? Maybe I instead want the version of this vector that's of length 1. We call it vector V or something. All right? Or maybe it's not length 1, but it's a vector that points in the same direction. Okay? If I'm describing R, one of the ways that I can describe R would be by using this formula. Okay? What this formula does is it says that I have a line that starts, or that contains the point R naught, that intersects this vector, we'll say, and based on the value of the parameter t, I move in the direction v. If t is positive, then I'm moving in the direction towards q. If t is negative, then I'm moving in the opposite direction. Okay, using the properties of vector addition, right? Because vector addition says that whenever I have two vectors, when I add them together, I add them tip to tail, right? Now, what this has the effect of doing, and is important to understand, is that the vector r here moves based on the value of t. What it's doing is tracing along this path. Okay, now that's a picture that's kind of hard to see in motion, but I try to do my best with the line drawer there. Does that make sense? Okay, so when we talk about lines in a 3D space, when we're using this vector notation, that's what we imagine is happening. I have this arrow that has been drawn, and this arrow is tracing the path of a line as t changes. So, like if you imagine that the tip of the arrow is a chisel or something, it's chiseling its path through space. Sorry, yes. T is, if I turn off my straight edge, T is a parameter. So it is allowed to take on the value of any real number. I hadn't said that yet. I meant to. Thank you for asking. Okay, so as t changes, that changes the direction and the terminal value of where our r vector is pointing. And so this line is characterized by this information here. I have some point that lies on the line. I have the direction that the line moves in, and I have a parameter t that tells me what all of the points are that lie on the line. Okay. Now, there are a couple of different ways to describe how this looks. If r naught is a vector whose coordinates are given by x naught, y naught, z naught, and the vector v, our direction vector, has coordinates a, b, c. Okay. And by the way, what this means is that these values here, if I put the origin as the beginning of the arrow and the end of the arrow ends at the point ABC. That is how this notation is interpreted. Okay? If R naught is given like this and V is given like this, then we can say that R has the coordinates x, y, z, where x, y, and z are given by x naught plus at, y naught plus bt, and z naught plus ct. What this allows us to do is instead write this as a system of equations. And these are called the parametric equations of a line. Make sense? All right. Now, as a simple example, we want to find the vector and parametric equations for a line. It's going to pass through the point 5, 3, 1. And it's parallel to I plus 4j minus 2k. So if we're told a point that the line passes through, then we can immediately write down what R naught is. Okay? And we can write this in either format. This is something that we should be very comfortable with. Okay. The other thing that we can do is immediately write down the direction vector of the line because we're told a parallel path to our vector. So it is just copying down this value here. Okay. No surprises. For the vector equation, we write down this expression, R naught plus TV. It doesn't matter if you write the workout here using component notation or canonical basis form. I'm just going to use canonical basis form. So we combine these things based on the I, J, and K. The work is done component-wise. So I distributed the T and regrouped. All right, all make sense? Okay, so this is the vector equation. To get the parametric equations, all we need to do is just take advantage of the work that we've already done. Make sense? Okay. If T is equal to 0, we have the point 531, which is what we expect, right? Because that's the point that we were told is on the line. We just plug it into the parametric equations, or we plug it in either here or here. It doesn't matter which one we use. T is equal to 1, then we get 6, 7, -1. Right? If T is equal to, say, -2, we're going to get 3, -5, +5. And so we have found other points that happen to lie on our line. Okay, so that's the role of t in this equation. You change the value of t, and you find any and all other points that lie on the line. Okay. The values here that show up, that are the ones that get multiplied by our parameter in the parametric equations, are sometimes referred to as direction numbers. So if the book uses that phrase, that's what's going on there. New page. Another important idea for lines is the idea of line segments. Okay? In our picture that we started off with, I had an origin point P and a terminal point Q, and I drew the line that passed through these 2 points. Okay? It may be the case, however, that what I want to represent is just the line that passes from one point to another and not worry about anything outside. We call that a line segment because it's a section here. In vector format, this vector that points from the origin to P would be R naught, and this vector that points from the origin to Q would be R1. Okay? And if we want to set this up and have the vector that traces out just this edge here of the line that goes from P to Q, then this vector R, which has t as a parameter, so this is a vector function of t. This previous expression that I wrote is also technically R of t. I just didn't write the of t part. We have this expression. Sorry, that's inclusive. Okay, so this is the equation of a line segment. The way this works is very straightforward. We allow t to range from 0 to 1. When t is 0, I'm just left with R1, or sorry, R naught, pardon me. Okay? When t is equal to 1, that goes to 0, and I'm just left with 1 times R1. Okay? All the values of t in between 0 and 1 put me in this middle part of the segment. Very useful expression here. Okay? Now you can simplify it and write down the parametric equations if you want, but usually the easiest way to think about this is in terms of the vector notation, because all I have to do is know my initial and terminal point. right? And if I reverse the initial and terminal point, does that actually matter? No, it's just I move along the segment the other direction, right? You got a question? The parameter, if you're talking about a line segment, the value of the parameter ranges from 0 to 1. Yes. So the difference between this picture and the picture that we had on the previous page is that if I restrict t from going in this range to go from 0 to 1 under this equation, I'm getting exactly this segment traced, starting at P and starting at and ending at Q. Before, if I don't have these restrictions, I can get the whole line extending past those edges. Now, if I take what I have here and I rip off this condition, I get the whole line back. It's a line that definitely passes through P and Q. All right, questions about this stuff? Seems okay? All right. Now, there is an important idea that comes up in 3D space that's not an issue in 2D space. Okay? If I'm in two-dimensional space, what has to be true about two lines that don't intersect? They have to be parallel, right? In 2D space, those are the only types of lines that can't intersect. In three-dimensional space, can I have non-intersecting, non-parallel lines? You can, right? I can have one line that's up here and another line that does this, and as long as they're not in the same plane, then, or if the planes that, okay, we'll talk about planes in a second, but if the planes that these lines live in are parallel, then they're going to be skew, is what we call this, okay? All right. Now, the way that you test to see if skew lines are skew is you use their parametric equations and you see if you can find an answer that makes sense. So for the first line, I'm not doing a specific example, I'm just kind of setting up what this would look like. What am I doing? Sorry, Y1, Z1. We'll call this alpha, I guess. All right. They're different lines, so they have to have different parameters. Okay, one of them depends on T, the other one depends on S, right? They also have different direction numbers, one given by ABC, the other one given by alpha, beta, gamma. And they also have different points that they pass through given by Y1, X1, Y1, Z1, and X2, Y2, Z2. The only things that are not known are the values of T and S. So what you do is you set this equal to this equal to this, and this equal to this, and see if you can find a T and S that works. If you can't, these lines are skew. System of 3 equations and 2 unknowns. It should be doable, right? Okay, that's what the process looks like. Okay, so you'll know all of these and all of these. So I know I wrote variables for everything, but there's the only T and S are the only unknown quantities there. Okie dokie. Let's keep going here. Planes. Plane is a flat two-dimensional surface that is typically embedded in a higher dimensional space. Okay. One of the things that we are going to have to understand when it comes to working in these higher dimensional spaces is that this as a plane is very clearly a two-dimensional object, right? You can think about it as a sheet of paper or something, right? One of the things that's weird, we'll talk about this more specifically later on, is if this is a sphere, okay, and when I talk about something being a sphere, I don't mean a solid. I mean something like a basketball that's been inflated to where the ball is just the skin of it, right? Both of these things are two-dimensional. Because if I'm standing here on this piece of paper and I'm only allowed to move in the directions that the piece of paper exists, how many directions can I really move? 2, right? I can, using 2 directions that aren't parallel, describe how to get to everywhere on that piece of paper, right? The same is true for a sphere. If I'm walking on the surface of a planet, because that's where we live, all right? We technically have 4 cardinal directions because there's north, south, east, and west, but north and south are really the same direction, just with a minus sign, and east and west are also really the same direction, just with a minus sign. So we only use 2, right? Or if we're being smarter about it, maybe we have a longitude and a latitude. It's definitely just 2. Okay? So we think about it as 3-dimensional because, yeah, there's like we can bury or we can dig underground or something like that. But in terms of the mathematical idea of a sphere, it's really 2-dimensional because there's only 2 directions of travel. Okay? If I draw some loopy curve thing, how many dimensions does that have? 1. I can move forward or backwards, right? And I can only move forwards or backwards because of the parameter that we use to describe what's going on. Because I could take this line, pull it taut, and it would have the same behavior as what I had before, right? So that's part of what we're building up to next chapter, technically, is dealing with these kinds of ideas. But it's best to start thinking about the consequences of dimensionality before we get there. Okay, so fundamentally, these things that we're working with are 2-dimensional. We're not worried about spheres right now. The thing we care about for the moment is the plane. Planes are described by two quantities, okay? All right, I need a point and I need a normal vector, okay? If I know where the plane is, or if, in order to know how to define a plane, what I need is a point on that plane and knowledge of the direction that is perpendicular to being on that plane. Okay? This perpendicular vector is what is known as the normal vector. All right. There are a couple of different ways to write this down. These are considered to be the vector equation of a plane. All right. And what this information tells us is this is a vector that lies in the plane. I have a point and I have a direction that lies in the plane. Okay. And then this normal vector is a vector that is perpendicular to all of the vectors that lie in the plane. Make sense? Okay. When we're working with this equation is a little bit awkward. So sometimes we will instead use the so-called scalar equation of a plane, where if the normal vector is given by ABC, and the point in the plane is x naught, y naught, z naught, then this expression here is what we call the scalar equation of a plane. I will draw attention to the fact, of course, that this and this say the same thing. If we interpret what the dot product is doing, right? Now, sometimes after distributing, these terms are collected and moved to the other side and just called D, technically minus D or whatever. And so you can write down a version of this expression that's just ax plus by plus cz plus d equals 0. By slightly transforming this equation as another way to write down what's going on with a plane. All right. Questions about this? Seems okay? All right. When it comes to finding normal vectors, we have to remember a very important property of cross products. If I take the cross product of two non-parallel vectors A and B, then that guarantees that the result of the cross product is going to be mutually perpendicular to both of those vectors. Okay, we have to remember our right-hand rule, right? So for those of you who are watching online, I'm holding up my right hand. Whatever way that you think about the right-hand rule is fine. You can either do sort of the finger gun method, where you point your index finger, you have to be careful about that, extend your thumb upwards, I guess, and then you have your middle finger, which points in the direction that your palm points in, okay? And so if you take A cross B, A being your index finger and B being your middle finger, then the resulting vector is the one represented by the thumb on your right hand, okay? Another way that you can imagine doing cross products, which is useful often in electricity and magnetism, is you use your right hand and you flatten out your hand so that your fingers are together and your thumb is extended outward and upward. And you put your thumb in the direction that you want the cross product to point, and then you curl your fingers around in the direction that you want the cross product to be computed. So the A is where your fingers are pointing. B is the direction that your hand curls when you close your fingers. And the end that you get, A cross B, is the direction that your thumb is pointing. This is useful because you can think about it as grabbing an electrical wire that current is flowing through. Okay? Flowing electricity generates magnetic fields. Magnetic fields are round, they're not straight. So the magnetic field that's generated by electricity flowing through a wire circles around the wire in the direction that your fingers are curling. If you imagine yourself as grabbing the wire with your thumb pointing in the direction of the current. I don't know if you've heard any about this, but that's another way to think about the cross product. Anyway, if you have non-parallel vectors A and B that lie in a plane, and you need the equation of a plane, you take their cross product. The cross product gives you the normal vector. You now have the equation of the plane. All right, that's how that goes. If you need to figure out information about planes or compare them, the way that you compare them is by their normal vectors. Planes are parallel if they have the same normal vector. The angle between planes can be determined by determining the angle between the normal vectors of those planes. All right, all of the relevant information is encoded in that normal vector. Okay, we didn't get quite as far today in chapter 12 as I'd like, but we will finish 12.6 next class. Next class is just a bunch of cases, but if we're smart about the way that we do it, we can cover that material pretty quickly. It's just a matter of setting up the equation correctly and then identifying the 3 or 4 different cases associated with the equation once it's in the right form. So we'll talk about that next time. Enjoy your day, and I will do what I can about getting the textbook sorted out.